Again, talking to us about how to build privacy-preserving machine learning, this time using a different technique, which is secure source outsourcing, right?
Good morning again. Before going into the details, a small disclaimer. Some of the content of this talk may be overlapping with the content of the first talk. Sorry for that. I'll try to quickly go through those things. So to begin with, the title of our talk is Blazing Fast Privacy-Preserving Machine Learning. This is a joint work with Arpita Patra of Indian Institute of Science, Bangalore. So the outline of the talk is as follows. Just a quick introduction to Secure Multiparty Computation, or MPC again. We'll see why the MPC for small number of parties, and in this case, for the case of 3 parties, why it is useful. And then an overview of our protocol Blaze in the 3-party setting, and we'll see some of our results in the domain of privacy-preserving machine learning. So Secure Multiparty Computation allows n parties to jointly compute function on their inputs without revealing their data, and the goals are correctness and privacy, where correctness guarantees parties are getting the correct output after the computation, and privacy guarantees that nothing more than the function output is revealed. And the problem can be tackled using a trusted third party, where parties can give their inputs to the trusted party, and trusted party performs the computation and gives the output back. But in reality, as I told before, we don't have such a trusted party, or in fact, it's very hard to get such trusted parties. So what we do is we use MPC to tackle this, where MPC emulates the function of this trusted party using the cryptographic techniques. In reality, there are parties who are corrupt, and we model the notion of these corrupt parties using an entity called adversary, where adversary controls all of these corrupted parties. And there are several traits of adversary, and one such trait classifies this adversary into 2 categories. One is called semi-honest, which one of the previous presenter has mentioned about, where the corrupt parties follows the protocol, but at the same time they are curious and tries to learn more about the underlying values. And a stronger security notion is called malicious, where the parties can arbitrarily deviate from the protocol. And in this work, we focus on malicious corruption. Coming to MPC for small number of parties, why it is useful is because of efficiency and simplicity. Efficiency means we can design very efficient protocols using symmetry primitives in this domain. And simplicity, we mean we can always instantiate a protocol which is designed for n parties by choosing n is equal to say 3 in this example. But when compared with those protocols which are designed for n parties when instantiated to a small party setting, we can actually make more efficient protocols by observing the nature of the parties. We know like there are 3 parties and there can be 1 corruption or 2 corruption like that. So based on those corruption scenarios, we can come up with nice protocols which are much better compared to instantiating a protocol designed for n parties to the small number of party setting. And in this work, as I told before, we are focusing on MPC with 3 parties, and the corruption is again on the honest majority. That means majority of the parties are honest, and for 3PC we can tolerate at most 1 corruption. Another interesting fact about MPC for small number of parties is it can actually solve MPC for a large population by the technique of outsourced computation. So here what we do is we hire a set of servers from among these parties or even from outside, and there will be a sharing semantics associated with this protocol scheme. Now the n parties, what they will be doing is they will distribute their data to this set of 3 servers in such a way that none of these servers will know the data in clear. And we design protocols for efficient computation among these 3 servers. They will perform the computation, and once the computation is over, the result will again be in a distributed fashion, and the final result will be reconstructed back to the designated parties. So this can solve, the MPC for small number of parties can solve this MPC for large population. Our protocols are cast in preprocessing model, which is a model that is considered for practically efficient protocols. So the first phase in this model is called a preprocessing phase, which is data independent, and this is relatively slow and expensive. With this data independent computation, next phase is the online phase, where when the actual data comes in, we perform this online phase. So in the online phase, the main target is minimize computation, and we want super fast computations happening in the online phase. Now coming to our protocol, Blaze. So before I go into the results, I will quickly give an overview of how a secret is shared in our protocol. So consider three parties, S0, S1 and S2, and we want to distribute this secret among these parties according to our protocol sharing scheme. So how it is done is, in the preprocessing phase, the first party, say S0, he will choose two keys and give one key each to each of these other two parties. S1 gets one key and S2 gets other key. Now with the keys set in the preprocessing phase, during the online, using the two keys and the data, what we will be computing is, we are basically locking the data using these two keys into a padlock, say. And this logged value will be, the log value will be given to both S1 and S2. So this is the first phase of sharing scheme, where the actual data is logged and the logged value is given to two of the parties along with one key each. Now there is another level of encapsulation which actually provide more efficiency to our protocol. In the second phase, once they get this, once S1 and S2 gets these log boxes, they will choose one key, which is the same key, and using that key they will encapsulate this log box further, and basically they will, it's called a double log. So they will log this logged box again using one other key which is available with both S1 and S2, and this will be given to S0. You can see the paper for details of this sharing scheme, why it is helping in achieving better efficiency compared to the state-of-the-art protocols. So this forms the overall sharing scheme in our case. So a data is shared as follows. There is a party who has two keys, and one of the keys will be available with two other parties. Now the data is first logged into a box, and the log box is available with both S1 and S2, and they will then choose a key, and using that key they will log this log box again and give that doubly log box to S0 back. So to analyze the efficiency of our protocol, we consider the communication cost per multiplication gate. So the work of Araki et al. In SP17, they came up with a 3PC protocol which require a communication cost of 12 elements in the pre-processing phase and 9 elements in the online phase, and they achieve a security of about. Later, Astra improved this result. Basically, they improved the online complexity from 9 to 4 elements by trading off the offline pre-processing complexity, and with an enhanced security of fairness, where in fairness the honest parties are guaranteed to get the output whenever the corrupt party receives the output. In 2019, in Crypto 2019, Bonnet et al. Came up with a 3PC protocol using the notion of distributed zero knowledge, where they showed how to achieve 3PC with a communication cost of 3 ring elements in the online phase and 0 in the pre-processing phase. And they have a security with abort. But this value of 3 is in the amortized sense. That means to get this value, you need several executions of the underlying 3PC protocol in parallel. Then only you can apply a technique of amortization, where the check corresponding to all these executions are cleverly combined, so that you will the cost of the check will amortize away. So this is the protocol by Bonnet et al. Which we use in our protocol. What we do is, we basically shift this Bonnet's protocol to the pre-processing phase. That's why we have a 3-element communication in the pre-processing phase. And we use all the distributed zero knowledge and the expensive primitives in the pre-processing, which is the data independent phase. Now with the pre-processing phase, with the data from the pre-processing phase in place, what we do is we again have a communication of just 3 ring elements in the online phase, and we achieve the enhanced notion of fairness. Here in our online phase, we don't require anything like distributed zero knowledge or any other expensive primitives. Ours is just XOR operations. Now I will simply skip through this privacy preserving machine learning part. So there is a model owner and client. They want to perform an algorithm, and for the privacy, if one of the party is corrupt, then he or she can learn the other party's input. And this is where what we do is we will combine the machine learning with MPC, and we call MPC meets ML. So in the privacy preserving machine learning, this is how the computation is performed. The model owner first distributes the model parameters to this set of 3 servers. Then the client will also distribute his query to this set of 3 servers. They will perform the computation using the underlying 3PC protocol, and the result is reconstructed back to the client. And in this work, what we considered is the following set of ML algorithms. We considered the training as well as prediction phase of linear regression and logistic regression, and we considered only the prediction phase of neural networks. Again, when it comes to PPML, it's not simply sufficient to just come up with a 3PC protocol. We need several primitives. One is secure dot product, another one is comparison, another one is a way of embedding the floating point numbers, which are actually the inputs to these ML algorithms, to this underlying ring. Then bit to arithmetic conversion, truncation, nonlinear activation functions, etc. So when we analyze the communication cost for a dot product, the work of ABY3, they require 12D elements in the offline and 9D elements in the online phase, and with the security of abort. And in Astra, they improved the cost from 9D to 2D plus 2 by trading off the pre-processing cost, but with enhanced security of fairness. And the work of Bonnet, they haven't provided a dot product protocol, but we can come up with a dot product protocol using their technique, and that will require a cost of 3D ring elements in the online phase. And in our results, since we are using this Bonnet's protocol in the pre-processing phase, we could shift this 3D communication to the offline, and using that data, we could achieve a communication in the online which is independent of the feature size. And this is achieved for the first time in the regime of this 3PC domain. And we also improve the security from abort to fairness. And this is a quick summary of our benchmarking results. So we have improvements from 27x to some 333x for linear regression, logistic regression, and neural networks. And these are some data from our paper. You can see the paper for the details due to time constraints. Yep. Questions?
All right. Sure. So we have time for perhaps 1 or 2 questions.
I don't think they have questions.
I have a question.
Yeah.
Seems like I think both of the techniques you presented, they try to secure the interactions, kind of protect privacy during the interactions between different parties, right?
Yes.
But at the end, the model, like if this is used for training, the model that you train could still be susceptible to different attacks, like privacy attacks.
Yes.
So how would you address that, or is it possible to kind of, I mean, how would you go about integrating those protections for those problems into your model? So
first of all, so far we haven't considered this adversarial model attacks or like machine learning stealing model attacks in our work. But currently we are working on that one. So one solution that we are trying to build is, so basically what happens is this, in this adversarial machine learning, they will query, and based on the result, they are trying to infer something about the underlying model.
Right.
Okay. But for those cases, the model are kind of static, and it's the same model that they are keep on querying. And there are some preventive attacks which limits the number of queries and all. And what we are currently thinking of is basically kind of retrain the model after a particular interval of time, so that the model parameters are now changed. So whatever queries they have collected so far becomes useless. It's not completely done yet, but we are currently working on that.
All right, sounds good. And there's also different kind of membership inference attacks that could try to steal the data set you use for training that model.
So we are currently working on that.
All right, sounds good. Thanks everyone for staying a few minutes longer. And let's thank the speakers one more time.
Thank you.